Valid values for RDS Global DB RPO range from 20 seconds to 68 years. Which organization is going to say, you know what amount of data loss is acceptable for us? 68 years. Yeah, go ahead, users of the application. You can just write to the application and we're just going to lose your data for the next 68 years. Before I play this video about me studying for the AWS Database Specialty Certification exam, I just wanted to let you know that I did pass the exam the day after making the video, and some parts of this video did help me with some parts of the exam. I talk about disaster recovery strategies for Amazon Aurora. I talk about RDS sharding. I talk about disaster recovery for RDS for SQL Server, and I talk about CloudFormation for DynamoDB auto scaling and KMS in cross-region situations. So I hope this video helps you in the exam as well. Ciao. What's up, fellow AWS learners? So I am learning something about AWS today because I am taking the AWS Database Specialty exam tomorrow, and I've been preparing for a while, but I am doing some last minute additional preparation. I pulled up this article on the AWS blog called the 10 study tips for the AWS Certified Database Specialty Certification, and I'm going to follow some of the tips. And I'm an auditory learner. So I like saying things out loud in order to process it. If I don't say it out loud, I can't process it. It's not that extreme, but pretty much. So if you learn by listening and you like listening to information while you're driving, I hope this helps you. I've done 11 AWS certifications already, and this will be my 12th one. So I'm pretty familiar with a lot of the concepts, but it's always good to refresh and also to dive a bit deeper in databases in particular. This is probably going to be a pretty long video just to go over a lot of information. One thing I thought was helpful in the links in this article was the link to the disaster recovery and Amazon Aurora global databases. So one thing they talk about in almost every AWS certification is the difference between RTO and RPO. So I think these are really good definitions compared to a lot of really lengthy definitions I see out there. So I'm going to read them out loud. Recovery time objective means downtime. And RPO, well, RPO means the amount of data lost in time, or the amount of data that can be lost measured in time. So objective just means a goal. So recovery time goal, recovery amount of data goal. So reading the full definition now, recovery time objective, RTO, the time it takes a system to return to a working state after a disaster. In other words, RTO measures downtime. For an Aurora global database, RTO can be in the order of minutes. Okay, so just think about that. How long can your database be down? Well, you kind of want it to never be down. But, traditionally it can take longer for databases to come back up. So, the organization might set a realistic goal of 1 hour or 2 hours. But since it's possible with Aurora Global Database, you can set a more aggressive goal that your database is only down for minutes. And then the recovery point objective, the amount of data that can be lost measured in time. For an Aurora Global Database, RPO is typically measured in seconds. With an Aurora PostgreSQL, I never know how to say that, PostgreSQL-based global database, you can use the RDS Global DB RPO parameter to set and track the upper bound on RPO. But doing so might affect transaction processing on the primary cluster's writer node. For more information, see Managing RPOs for Aurora PostgreSQL-based global databases. That's interesting. So, wow, okay, RPO is typically measured in seconds. So I guess that means they take a lot of backups, because then you can go back to a specific second. So with an Aurora PostgreSQL-based global database, you can use the RDS Global DB RPO parameter to set and track the upper bound on RPO. Interesting. I don't really know what that means. So I'm gonna open up the text edit and we're gonna come back to that. For more information, we'll come back to this link to understand that parameter a bit more. Let's finish this page of documentation and then we'll get to that. So within Aurora Global Database, you can choose from two different approaches to failover: managed planned failover and unplanned failover. So the managed planned failover, so that's a feature? Is that a feature? Yep, this is a feature. It's intended for controlled environments such as disaster recovery, testing scenarios, operational maintenance, and other planned operational procedures. Managed planned failover allows you to relocate the primary database cluster of your Aurora Global Database to one of the secondary regions. Because this feature synchronizes secondary database clusters with the primary before making any other changes, RPO is 0, no data loss. RTO for this automated process is typically less than that of the detach and promote failover process because the demotion, promotion, and all synchronization are handled for you. To learn more, see Managed Planned Failover for Amazon Aurora Global Databases. We'll come to that link later. I think this is really a beautiful definition. Like, sometimes I just want a really short definition, even if it's not the complete definition, but you see some really long definitions of RTO and RPO, and I kind of like this one. RTO, downtime. RPO, data loss. Okay? So I'm going to stick with that in my head. Unplanned failover, detach and promote. To recover from an unplanned outage, you can perform a cross-region failover to one of the secondaries in your Aurora Global Database. The RTO for this manual process depends on how quickly you can perform the tasks listed in recovering an Amazon Aurora Global Database from an unplanned outage. The RPO is typically measured in seconds, but this depends on the Aurora storage replication lag across the network at the time of the failure. Okay, the RPO depends on the storage replication lag at the time of the failure. Good to know. I'll just say that one more time. The RPO depends on the storage replication lag at the time of the failure. So this article goes on to talk about managed planned failover for Amazon Aurora Global Databases and recovering an Aurora Global Database from an unplanned outage. Okay, so I think these other sections are the sections that we're linked to here up above. So let's get into it. Managed planned failover for Amazon Aurora Global Databases. By using managed planned failover, you can reload. Okay, I'm actually going to go back here. I want to understand this. To recover from an unplanned outage, you can perform a cross-region failover to one of the secondaries in your Aurora Global Database. The RTO for this manual process. So I'm trying to understand, why is this a manual process? You know, you've got a global database. I would expect there to be a health check and it can kind of just fail over automatically. But it says here a manual process is what you got to do when there's an unplanned failover. So that's a question mark I have here. I'm gonna write down that question and come back to it. Why is unplanned failover defined as a manual process in the guide to recovering Aurora Global Databases? Can't an Aurora Global Database be recovered automatically in the case of a disaster? So moving on, now that I have more clarity around what my unclarity is, managed planned failover for Amazon Aurora Global Databases. By using managed planned failover, you can relocate the primary cluster of your Aurora Global Databases to a different AWS region on a routine basis. Being able to demonstrate this capability with your production system is a legal requirement for government agencies, financial institutions, and many other regulated industries. This feature is intended for controlled environments such as disaster recovery, DR, testing scenarios, operational maintenance, and other planned operational procedures. Okay, that makes sense. So if you're a bank and you've got thousands or millions of customers relying on you for money, then you are held up by the law to say, we've tested that our database can recover to a different region if necessary. We've done the test. So that's what this testing capability is for. As an example, say a financial institution headquartered in New York has branch offices located in San Francisco, in the UK, and in Europe. The organization's core business applications use an Aurora global database. Its primary cluster runs in the Ohio region, with secondary clusters running in the US West, Northern California region, London, and Frankfurt regions. Every quarter, it relocates the primary cluster from the current primary AWS cluster to the secondary region designated for that rotation. Oh, okay. So that's an interesting approach. I thought that with a global database, you would just, temporarily move the primary cluster to a different region, and if it works, you move it back. But according to this, another approach could be having a rotation where with every period of time, like every quarter, the primary cluster is in a different region. So that's an interesting approach. Moving on. Not every organization needs to rotate their Aurora global database's primary cluster on a regular basis. However, the ability to do so during an audit by regulators is a key requirement to meeting disaster recovery requirements. We recommend managed planned failover for organizations of all types as a best practice for DR preparedness. This not only ensures that your procedures are complete and accurate, but more importantly that staff are trained to perform a DR failover before it really happens. Right, because I guess people are involved, since my question said, is there really manual steps involved? Okay. Managed planned failover is designed to be used on a healthy Aurora global database. To recover from an unplanned outage, follow the detach and promote process detailed in recovering an Amazon Aurora global database from an unplanned outage. Okay, right. So we're going to get to that soon. During a managed planned failover, your primary cluster is failed over to your choice of secondary region, while your Aurora global database's existing replication topology is maintained. Before the managed planned failover process begins, Aurora global database synchronizes all secondary clusters with its primary cluster. Okay, so I guess the secondary clusters are synced on a regular basis, but there's one more sync that happens right before the failover when it's a planned failover. And that's why it says there's 0 seconds RPO. Is that how you call it? 0 seconds RPO? Yeah, the RPO is 0. And since RPO is measured in time of data loss, I can say seconds or minutes or hours, it's still the same old 0. The sync happens right before a managed failover to ensure that RPO we're talking about is 0 time. The database cluster in the primary region becomes read-only. Okay, the database cluster in the primary region becomes read-only. Okay, right. So when a primary cluster is no longer a primary cluster, then it's a read-only. The chosen secondary cluster promotes one of its read-only nodes to full writer status, thus allowing the cluster to assume the role of primary cluster. Okay, so what makes a primary cluster and not a secondary cluster? The fact that one of its nodes is a writer node. Okay, so because all secondary clusters were synchronized with the primary at the beginning of the process, the new primary continues operations for the Aurora global database without losing any data. Okay, that was a long sentence. Let me try to understand that. Because all secondary clusters were synchronized with the primary at the beginning of the process, the new primary continues operations for the Aurora global database without losing any data. Right. That's the same thing we said already a few times. There's a sync, and because the sync happens right before, there's no loss of data. So your application is unavailable for a short time. So that's RTO. So there is a few seconds. You can have a recovery time objective, the amount of downtime of a few seconds, but a recovery point objective, the amount of data loss measured in time of 0. So again, your application is unavailable for a short time as the primary and selected secondary clusters assume their new roles. So you're not going to lose any data, so maybe have your data coming into your application in a queue, where it can stay there for those seconds waiting for the database to be up, and then those transactions can be written to the database once the secondary has been promoted to the primary. Okay, moving on. To optimize application availability, we recommend that you do the following before using this feature. Perform this operation during non-peak hours or at another time when writes to the primary DB cluster are minimal. Right, so these are some tips for doing the managed planned failover for Aurora global databases. Since there are a few seconds of downtime, why do that when you have the most amount of transactions? So if you have more transactions during a certain time of day, don't do the managed planned failover during your peak time. Take applications offline to prevent writes from being sent to the primary cluster of Aurora global database. Yeah, I guess you could just say, okay, downtime, don't do anything on this application during those few seconds. But if you want to be more fancy, probably you can set up some sort of queuing system. So the next tip here is check the lag times for all secondary Aurora DB clusters in the Aurora global database. So this is, again, one of those things where the documentation is written for huge organizations, because not a lot of businesses are going to have Aurora DB clusters in like a lot of regions. Most people are going to have just one secondary DB cluster in a disaster recovery region. But if you have several secondary Aurora DB clusters, then choose the time with the least overall lag time for the managed planned failover. These are very long phrases sometimes. Use Amazon Cloudwatch to view the Aurora Global DB replication lag. Say that 10 times fast. Aurora DB replication lag. Aurora Global DB replication lag metric for all secondaries. This metric tells you how far behind in milliseconds a secondary is to the primary DB cluster. Its value is directly proportional to the time it'll take for Aurora to complete failover. In other words, the larger the lag value, the longer the outage. So choose the region with the least lag. Okay. So there is a way to have a logic behind which region you choose for failover, and that is which one is going to give you the least downtime when you do the failover. And how do you figure out which one gives you the least downtime? By looking at which one has the lowest value in the Aurora Global DB replication lag metric in Cloudwatch. For more information about Cloudwatch metrics for Aurora, see cluster level metrics for Amazon Aurora. Whew, that was a mouthful. During a managed planned failover, the chosen secondary DB cluster is promoted to its new role as primary. However, it doesn't inherit the various configuration options of the primary DB cluster. A mismatch in configuration can lead to performance issues, workload incompatibilities, and other anomalous behavior, such as your database engineers being sad. To avoid such issues, we recommend that you resolve differences between your Aurora global database clusters for the following. Configure Aurora DB cluster parameter group for the new primary if necessary. Okay. Yeah. How do you avoid there being a misconfiguration? By configuring it. Okay. Yeah, that's a good tip. No, but let's see what the details are on that tip. So you can configure your Aurora DB cluster parameter groups independently for each Aurora cluster in your Aurora global database. I'm about to stop saying the word Aurora here because that's a lot of Auroras in one sentence. That means that when you promote a secondary DB cluster to take over the primary role, the parameter group from the secondary might be configured differently than for the primary. If so, modify the promoted secondary DB cluster's parameter group to conform to your primary cluster settings. To learn how, see modifying parameters for an Aurora global database. Okay, so basically, when they talk about configurations being different between secondary clusters and the primary cluster, one of the things they're talking about here is the parameter groups of the Aurora cluster. If those are different, that can lead to issues that are unexpected and performance issues. So make sure before you do the managed planned failover that the secondary cluster that you are promoting to primary has the same parameter group configurations as the primary. Configure monitoring tools and options. such as Cloudwatch events and alarms. Configure the promoted DB cluster with the same logging ability, alarms, and so on as needed for the global database. As with parameter groups, configuration for these features isn't inherited from the primary during the failover process. Well, that makes a lot of sense. I mean that it's not inherited because Cloudwatch is a separate service, so you have to configure it separately. Of course, that's why you would want to have all your resources deployed using some sort of automation like CloudFormation or CDK or Terraform, because that way you can use the same template to deploy to all your secondary clusters, and then you automatically have the same alarms and so on and logging for all of those clusters. And then the third tip for avoiding surprising things happening due to inconsistent configurations between the clusters, the third tip is configure integrations with other AWS services. Well, if your Aurora Global Database integrates with AWS services such as AWS Secrets Manager, AWS IAM, S3, and Lambda, you need to make sure these are configured as needed. Okay, I think that's, a pretty big duh, but I guess, humans make mistakes and it's good to have a checklist. So, if your application was having the database integrate with Lambda, make sure it integrates in the secondary region as well. When the failover process completes, the promoted DB cluster can handle write operations for the global database. You can change the endpoint for your application to use the new endpoint. If you accepted the provided names when you created the global database, you can change the endpoint by removing the RO from the promoted cluster's endpoint string in your application. Okay. So if you already had the secondary cluster's endpoint string in your application, the only difference after it's promoted is it's not read-only anymore, so you can take off the -RO. I think that's what this means. Let's see. For example, the secondary cluster's endpoint my-global.cluster-ro-west-1.rds.amazon-aws.com becomes the same thing without RO. So my global cluster US West 1 RDS Amazon AWS.com when that cluster is promoted to primary. You can fail over your Aurora Global Database using the AWS Management Console, the CLI, or the RDS API. Alright, so basically what they're saying here is there's a naming convention. A secondary cluster is always going to have an RO in the default name provided by AWS, and that tells you it's a read-only cluster, aka a secondary cluster. And when it becomes the primary cluster, that RO goes away. And you can depend on that, is what they're saying here. So here is some documentation on how to do it in the console, in the CLI, in the API. I kind of want to see it in the CLI, to be honest, because that tells you what all the steps are. And I see here there's just one single step. And that's why I wanted to see that in the CLI, is because sometimes things can take a few clicks. So you gotta click on status. I mean, it looks pretty quick, but it takes longer to explain in pictures and words than a single CLI command. So I'm gonna look at the CLI command. Use the Failover Global Cluster CLI command to fail over your Aurora Global Database. With the command, pass values for the following parameters. Region. Specify the AWS region where the primary DB cluster of the Aurora Global Database is running. I can't say Aurora anymore. Specify the region where the primary DB cluster of the global database is running. And then the next parameter for the Failover Global Cluster CLI command is Global Cluster Identifier. Specify the name of your Aurora Global Database. And the next and third Failover Global Cluster CLI command parameter is Target DB Cluster Identifier. Specify the ARN of the DB cluster that you want to promote to be the primary of the global database. Okay, so basically to do the failover, it's just one command in the CLI if you want to do it via the CLI, and you just got to say what region is the primary cluster running in, what is the name of the global database, and what's the ARN, the identifier basically, of the cluster that you want to make primary. So that makes sense. Nice and straightforward. Managing RPOs for Aurora's PostgreSQL-based global databases. Okay, so now we're getting into the territory of RDS parameters. And that was the question I had earlier. What does the RDS global DB RPO parameter really do? I mean, it told us it sets and tracks the upper bound on RPO, but what good does it do us that that parameter is tracking the upper bounds in practice? So let's see what this means. With a PostgreSQL, so I'm not going to say Aurora PostgreSQL every time, but I'm talking about Aurora PostgreSQL. So with a Aurora PostgreSQL-based global database, you can manage the recovery point objective, RPO, for your Aurora global database by using PostgreSQL's RDS.globalDB_RPO parameter. RPO represents maximum amount of data that can be lost in the event of an outage. So once again, I'm just going to say it over and over for my own sake. RTO means maximum acceptable downtime. RPO means maximum acceptable data loss measured in time. So RPO represents maximum amount of data that can be lost in the event of an outage. When you set an RPO for your PostgreSQL-based global database, Aurora monitors the RPO lag time of all secondary clusters to make sure that at least one secondary cluster stays within the target RPO window. RPO lag time is another time-based metric. Okay, so how does it make sure that at least one secondary cluster stays within the target RPO window? And why do it only for that one? Why not for all of them? So hopefully we'll get an answer below here. The RPO is used when your database resumes operations in a new AWS region after a failover. Aurora evaluates RPO and RPO lag times to commit or block transactions on the primary as follows. Commits the transaction if at least one secondary DB cluster has an RPO lag time less than the RPO. Okay, so we're getting into the weeds of the internal Aurora logic around RPO. So I'm going to read that again because this is a little bit more complex, at least in my head at this moment. The RPO is used when your database resumes operations in a new AWS region after a failover. Aurora evaluates RPO and RPO lag times to commit. So what's the difference between RPO and RPO lag times? RPO represents the maximum amount of data that can be lost in the event of an outage. Aurora monitors the RPO lag time of all secondary clusters to make sure at least one secondary cluster stays within the target RPO window. So RPO lag time is another time-based metric. Okay, so I'm still trying to understand what's the difference between RPO and RPO lag time, because it looks like those are two separate things. How far behind the RP goal, the RPO, how far behind the recovery point objective is the application lagging? That would make sense. Let's say the organization sets a really aggressive RPO of 2 seconds and then the cluster in one of the secondary regions is lagging behind the RPO by 2 seconds. So it's at 4 seconds in total. And then in another region, let's say Seoul, it is lagging behind the RPO by 5 seconds, so a total of 7 seconds RPO. So that's my guess. Let's see if we'll find out. So Aurora evaluates RPO and RPO lag times to commit or block transactions on the primary as follows. Okay, so it uses these RPO and RPO lag times. It actually uses the recovery point objective that you as an organization set and configure in your global DB RPO parameter in the following way. It commits the transaction if at least one secondary DB cluster has an RPO lag time less than the RPO. Okay, so that's basically a negative number. If the RPO lag time is a negative number, then you're doing better than the objective that you set for yourself in terms of your recovery point. So the second way in which Aurora evaluates RPO and RPO lag times to commit or block transactions is it blocks the transaction if all secondary DB clusters have RPO lag times that are greater than the RPO. It also logs the event to the PostgreSQL log file and emits wait events that show the blocked sessions. What? Okay, let me dig into that. Aurora blocks the transaction. Okay, like someone's trying to write, and it blocks it if all secondary DB clusters have an RPO lag. Okay, gotcha. If it also logs the event to the PostgreSQL log file and emits wait events that show the blocked sessions. Okay, so when does that happen? It says here it's used after a failover, but why would you block transactions after a failover? It blocks the transaction if all secondary DB clusters have an RPO lag time. Like, wouldn't you want to block managed failover if the RPO for all secondary DB clusters are greater than the RPO? So hopefully that question will be answered below here. In other words, if all secondary clusters are behind the target RPO, Aurora pauses transactions on the primary cluster until at least one of the secondary clusters catches up. Transactions are committed again as soon as the lag time of at least one secondary DB cluster becomes less than the RPO. The result is that no transactions can commit until the RPO is met. Okay. So maybe this means that you want to at all times be able to fail over and do so within the time objective you set as your organization. And if all the secondary clusters are lagging behind, then you should probably also on your primary cluster say, whoa, like let's cool it a little bit on the application on all this transacting until the others have caught up a bit. Because if there is a downtime with the primary now at this point, then the secondary databases, the secondary clusters are too far behind. They are further behind than is acceptable for our organization. So I think that's what that means. If you set this parameter as outlined in the following, you can then also monitor the metrics that it generates. You can do so by using PSQL or another tool to query the Aurora Global Database's primary DB cluster and obtain detailed information about your PostgreSQL-based global databases operations. To learn how, see monitoring Aurora PostgreSQL-based Aurora global databases. I am kind of curious about how that works, so I'm going to make a note about that. So to learn how to use PSQL, oops, no, I really did mean PSQL. Thank you, autocorrect. To learn how to use PSQL to monitor the RPO and RPO lag, see. Okay, so we can come back to that. And then setting the recovery point objective. Okay, so now we're getting into the details of the value to use for that, I guess, and how to set it, how to set this parameter. The RDS global DB RPO parameter controls the RPO setting for a PostgreSQL database. Yeah, we got that. This parameter is supported by Aurora PostgreSQL, right? Like you're not gonna get a global DB RPO parameter supported by off-the-shelf PostgreSQL. Valid values for RDS global, right? You're not gonna get it supported by just your generic open source PostgreSQL. This is a Aurora global DB parameter. Valid values for RDS global DB RPO range from 20 seconds to 68 years. Which organization is going to say, you know what amount of data loss is acceptable for us? 68 years. Yeah, go ahead, users of the application. You can just write to the application and we're just going to lose your data for the next 68 years. So that's a very generous range here. Very open-minded range, non-opinionated range. And then it's interesting that 20 seconds is the lowest one they provide. So I guess they're expecting that the global DB RPO is not really going to realistically be less than 20 seconds. So that's That's really insightful there. And it says choose a realistic value to meet your business need and use case. For example, you might want to allow up to 10 minutes for your RPO, in which case you set the value to 600. Right, because 10 times 60 is 600. And you can set this value for your PostgreSQL-based global database by using the console, the CLI, or the RDS API. And again, I'm going to take a look at the CLI. To set the RDS global DB RPO parameter, use the modify DB cluster parameter group CLI command. In the command, specify the name of your primary cluster's parameter group and values for the RPO parameter. Yeah, okay, so I don't want to hear an explanation about the command. I just want to see the command. Basically, the command is AWS RDS modify DB cluster parameter group, and then the DB cluster parameter group name, such as my customer. Oh, why can't I see this whole thing? There we go. DB cluster parameter group name, my custom global parameter group. And parameters, parameter name equals RDS global DB RPO. Parameter value equals 600, and apply method immediate. Cool. So if we want to check that value, if we want to view the recovery point objective that we set, we can look at the parameter which is stored in the DB cluster. The recovery point objective RPO of a global database is stored in the RDS global DB RPO parameter for each DB cluster. You can connect to the endpoint for the secondary cluster you want to view and use PSQL to query the instance for this value. Okay, so you go into that database and you say show rds.globaldbrpo. If this parameter isn't set, the query returns the following: -1 row. This next response is from a secondary DB cluster that has 1 minute RPO setting. So it'll say 60 because it returns the response for global DB RPO in seconds. You can also use the CLI to get values for find out if I weren't in the middle of a video, I would submit a pull request to correct this typo. Because did you know that all of the AWS documentation is on GitHub? Yes, that's right. You can make contributions to the AWS documentations yourself if there's something you want to improve. And I have done so for a couple pieces of documentation before. So you can use the CLI to get values for finding out if RDS Global DB RPO is active on any of the Aurora DB clusters by using the CLI to get values of all user parameters for the cluster. AWS RDS describe DB cluster parameters, DB cluster parameter group name, lab test APG global source user. And I kind of wonder, does that mean a user as in a database user? So does the RDS CLI have any sort of interface for database users? So it says here, AWS RDS describe DB cluster parameters, and then it has two parameters, the DB cluster parameter group name and source user. So I'm actually pretty curious about this, so I'm gonna look up the documentation for this command and see what they really mean by the user here. The source, it's a value that indicates to return only parameters for a specific source. Parameter sources can be engine, service, or customer. So was this engine, service, or customer in this case? So we had source user. I guess that means customer. So I still want to understand a little bit more about that, but let's see what the examples here are. So I'm going to leave that as an open question mark and come back to that later. So for this, what does source user mean in practice? The command returns output similar to the following for all user parameters that aren't default engine or system DB cluster parameters. Another typo, two typos. Okay, so the output that the command returns is parameter name, RDS global DB RPO, parameter value 60, description, recovery point objective, source user, apply type dynamic, data type integer, allowed values. Oh, from 20 seconds to, what was it, like 68 years, is modifiable true. You can change the RPO at any time. Apply method immediate, supported engine modes provisioned. To learn more about viewing parameters of the cluster parameter group, see viewing parameter values for a DB cluster parameter group. Next, we have a section about how to disable the recovery point objective. What if you no longer want to have a recovery point objective? Because as we heard, one of the effects of having a recovery point objective is that Aurora is going to block transactions to the primary if all of the secondary clusters are lagging behind. So to disable the RPO, reset the parameter. Reset the RDS global DB RPO parameter. You can reset that using the console, the CLI, or the API. So with the CLI, you would do AWS RDS reset DB cluster parameter group, and then you select the DB cluster parameter group name, and you provide the parameters that you want to reset. So RDS global DB RPO and apply method immediate. And then we have the last section of this pretty long page, recovering an Amazon Aurora global database from an unplanned outage. Now this is the real stuff here. When a real accident happens, I like how they say on very rare occasions, and it's true, So on very rare occasions, your Aurora global database might experience an unexpected outage in its primary AWS region. If this happens, your primary Aurora DB cluster and its writer node aren't available, and the replication between the primary cluster and the secondaries ceases. Basta, nada, nothing, zilch. To minimize both downtime, RTO, and data loss, RPO, you can work quickly to perform a cross-region failover and reconstruct your Aurora global database. Yeah, I'm sure you want to work quickly in that situation where your primary database cluster went down, but I'd rather have automation to do that for me. So I'm still having that question in the back of my mind. How do you automate that whole thing? Okay, we get a little blue box with a tip. We recommend that you understand this process before using it. Have a plan ready to quickly proceed at the first sign of a region-wide issue. Like doing a fire drill, or like understanding what to do in the case of a disaster. Same thing, you want to understand how to do this so you can do it quickly. Be ready to identify the secondary region with the least lag time. Use Amazon Cloudwatch regularly to track lag times for the secondary clusters. Right, you want to be ready to see, oh, this is the secondary region with the least lag time. This is the one we're choosing. So, get used to tracking those lag times and looking at them. To fail over to a secondary cluster after an unplanned outage in the primary region, do the following 6 steps. Step 1, stop issuing drop and roll. No, just kidding. Not stop, drop, and roll. Stop issuing DML statements and other write operations to the primary Aurora DB cluster in the AWS region with outage. Okay, yeah. Like, if your primary database goes down, stop trying to write to it. I just want to get a refresher on what exactly DML stands for. It stands for Data Manipulation Language. So stop issuing data manipulation language statements and other write operations. Doesn't that just mean like a SQL statement? Yeah, like SQL. So the second step after, telling your app to stop writing to the broken database, or maybe broken isn't the right word, but yeah, I guess if it's not working, it's broken. 2, identify an Aurora DB cluster from a secondary AWS region to use as a new primary DB cluster. This secondary cluster looks nice. It has a very low lag time. If you have 2 or more secondary AWS regions in your Aurora global database, choose a secondary cluster that has the least lag time. Third step in this disaster situation, detach your chosen secondary DB cluster from the Aurora global database. What? The third step is to detach your chosen secondary DB cluster from the Aurora global database? Like, bye-bye? Why detach it? So the next paragraph explains this, I think. Removing a secondary DB cluster from an Aurora global database immediately stops the replication from the primary to this secondary and promotes it to a standalone provisioned Aurora DB cluster with full read-write capabilities. Any other secondary Aurora DB clusters associated with the primary cluster in the region with the outage are still available and can accept calls from your application. They also consume resource. Since you are recreating the Aurora global database, to avoid split brain and other issues, remove the other secondary DB clusters before creating the new Aurora Global database in the steps that follow. For detailed steps for detaching, see removing a cluster for an Amazon Aurora Global database. Okay, this is kind of surprising to me. Like, why doesn't AWS do that for you? I really wish it said here, you can do this manually, or you can just trust AWS to choose the secondary cluster, do the detaching, do the reconfiguring for you. Like, why is that not written here? I thought that was an option, but I guess not. I mean, at least the tools are here so that you can do it manually really quickly. So the next step here is to reconfigure your application to send all write operations to this now standalone Aurora DB cluster using its new endpoint. If you accepted the provided names when you created the Aurora Global database, you can change the endpoint by removing the RO from the cluster's endpoint string in your application. For example, the secondary cluster's endpoint, my global cluster -ro US West 1 RDS Amazon AWS.com becomes my global.cluster without the RO when that cluster is detached from the Aurora Global database. Okay. So promoting a secondary cluster from read-only to a writer capable cluster basically means detaching it from your global database. This Aurora DB cluster becomes the primary cluster of a new Aurora Global database when you start adding regions to it in the next step. Okay, so we detached the secondary cluster that we want to use as our new primary cluster, and now we're going to make it a global database again. We're going to attach the secondary clusters from the other regions to it. So add an AWS region to the DB cluster. When you do this, the replication process from primary to secondary begins. For detailed steps to add a region, see adding an AWS region to an Amazon Aurora Global database. And the sixth and final step, add more AWS regions as needed to recreate the topology needed to support your application. Okay, so I guess there's a temporary thing when you're doing the manual unplanned recovery where it's not a global database anymore on your new primary cluster, and then you add back the other regions and then it becomes a global database again. Make sure that application writes are sent to the correct DB cluster before, during, and after making changes such as these to avoid data inconsistencies among the DB clusters in the Aurora Global database. We're talking about split brain issues here, folks. If you perform this reconfiguration in response to an outage in an AWS region, you might be able to return your Aurora Global database to its original primary AWS region after the outage is resolved by using the managed planned failover process. Okay, so what this is saying is, if there's an outage, you need to do the above 6 steps to make one of your secondary region clusters the new primary cluster. But once the outage is over, you might want to make the region that previously had the primary cluster, you might want to make that the primary cluster again. And for that kind of switch back, for that return to the ways of old, you can use the steps we went over before for the managed planned failover. So your Aurora Global database must use a version of Aurora PostgreSQL or Aurora MySQL that supports the managed plan over failover feature. Oh, whoa, okay. So if you want to be able to do all of the above, choose the correct versions. Choose a version that supports all this. So we finished that long page on disaster recovery and Amazon Aurora Global databases. And before we move on, I just want to briefly Google, is there any way to do the unplanned failover automatically? How to do unplanned failover with Aurora Global databases automatically. Managed planned failovers must include the word automatically. There's a word automatically here. Automatically. Okay, here's a word. The Aurora storage system automatically maintains 6 copies of your data across 3 availability zones within a single region, and automatically attempts to recover your database in a healthy availability zone with no data loss, which significantly improves durability and availability. Yeah, so that's kind of the behavior I'm expecting on a global scale too, that it automatically attempts to recover the database on a global scale by doing all those steps of detaching the secondary cluster based on which secondary cluster has the lowest lag time. Yeah, that's kind of what I was hoping to see here. Let's see. So to recover from an unplanned outage, you can manually perform. So again, no mention of automatic recovery. Aurora global databases. So here I found something that looks kind of like what I was thinking when I read the documentation. Global database seems really weird. To promote a failover region, you need to remove it from the global cluster and you create a new global cluster. This seems really weird. I don't actually understand what global database offers if I have to manage replication change. Yeah, that's the thought I had. So Li Ju said that he is yet to find a globally replicated database that handles failover automatically. So Li Ju is saying that, yeah, even though this seems like something that it would be nice AWS handled it, there isn't a better option out there. And then product manager with the Amazon Aurora team said, sorry to hear, those are your thoughts, thanks for the feedback. And then someone else said, yeah, this is a very painful process to have to go through 10 different steps, like removing the secondary cluster you want to promote from the global database and then creating a new global database and then re-adding them. And that's where that thread ended. So, okay, that was a nice reality check for me that I'm not the only one thinking like, wow, these are a lot of manual steps to promote the secondary cluster to primary in the event of an unplanned outage. But as one person pointed out, there doesn't seem to be a better solution out there. So it's at least good to know what's involved. So the next blog post on the 10 study tips for the AWS Certified Database Specialty Certification that is mentioned here that I am interested in is the cross-region disaster recovery of RDS for SQL Server. So this blog post, Cross-Region Disaster Recovery of Amazon RDS for SQL Server, was written by Changbin Gong and Rajiv Totatil on the 27th of July 2020, and it's with the categories Amazon RDS, RDS for SQL Server. Amazon RDS for SQL Server makes it easy to set up, operate, and scale SQL Server deployments in AWS for your enterprise workloads which depend on RDS for SQL Server. You need an effective disaster recovery strategy to help you stay up and running if an unexpected event occurs. This post discusses how to create a reliable cross-region disaster recovery strategy for RDS with SQL Server. So as I read this, I'm going to be curious to see how this compares to doing a cross-region disaster recovery strategy using Aurora global databases for PostgreSQL and MySQL. Disaster recovery strategy considerations. When you create a disaster recovery strategy for RDS for SQL Server in the AWS cloud, you should consider several factors. First, you need to understand how DR changes in the AWS cloud. Typically on-premises customers set up synchronous replication for SQL Server in a single data center where they are preventing hardware failure. And they set up either an asynchronous replication or a snapshot in a different data center or possibly a different site. AWS provides you with the flexibility to place instances and store data within multiple geographic regions and across multiple AZs within each AWS region. RDS for SQL Server provides a multi-AZ deployment which replicates data synchronously across AZs. This highly available multi-AZ deployment is usually sufficient for a DR strategy within one region in an AWS cloud environment. In addition, with the in-region read replica capability of RDS for SQL Server, you can use read replicas as a warm standby solution in a different AZ. This provides another in-region DR strategy. Alright, so it sounds like they say we have two in-region DR strategies. I understand the one that we've got the read replica capability of RDS, but what is the other one? So there's the option of having a multi-AZ deployment, which replicates data synchronously across AZs, and there is the in-region read replica solution. So I guess a highly available multi-AZ deployment which replicates data synchronously across AZs sounds like an active configuration, and the warm standby solution sounds like just that. And looks like there's another blog post that goes into more depth about that, but we can come back to that later. Before you consider a cross-region DR strategy, you need to evaluate whether an in-region DR solution meets your needs or not. Recovery point objective, RPO, recovery time objective, RTO, and cost are 3 key metrics to consider when developing your DR strategy. Yeah, it's important to throw in cost there because obviously with enough money, you can get your RPO and RTO lower. Based upon these 3 metrics, you can define your DR strategy ranging from a cold DR, which means backup and restore, to a hot DR, active to active. A reliable and effective cross-region DR strategy keeps your business in operation with little or no disruption, even if an entire region goes offline. Cross-region DR strategy. A cross-region DR strategy consists of 2 approaches: snapshot and restore, and continuous replication. Snapshot and restore. Oh, okay, so are those 2 different strategies? Looks like it. So with the snapshot and restore option, if you have less stringent RTO and RPO requirements for your RDS SQL servers, using cross-region snapshot and restore is one of the most cost-effective cross-region DR strategies. In your source region of your Amazon RDS for SQL Server, you can perform the following 2 actions. Create snapshots of your RDS for SQL Server based upon a predefined schedule. Copy the snapshots to your DR region. The frequency of snapshot copying is determined based on the RPO requirement. Okay, so the 2 steps are create a snapshot and copy the snapshot to the other region. When you test or execute your DR plan, in case of a disaster, you can restore the snapshot to a new RDS for SQL Server instance. The time to create a manual snapshot on your primary SQL Server is one of the factors that determines what a minimum RPO value is possible in your environment. The amount of time it takes to create a snapshot varies with the size of your databases. The first snapshot of a DB instance contains the data for the full DB instance. Subsequent snapshots of the same DB instance are incremental, which means that only the data that has changed after your most recent snapshot is saved. If you have a very small RPO that requires more frequent DB snapshots, you need to consider a different DR strategy, such as cross-region continuous replication. So I don't understand the logic there that if you need more frequent DB snapshots, that you should consider a different DR strategy, such as cross-region continuous replication. The reason I don't understand that logic is because it just finished saying that subsequent snapshots are incremental. So that seems like, if it's incremental, you can make as many snapshots as you want. So maybe that'll be clarified later in the article. Depending on the regions involved and the amount of data to be copied, a cross-region snapshot copy can take hours to complete. You need to take this factor into account when you estimate the RPO of this DR strategy. You can copy a snapshot that has been encrypted using an AWS KMS encryption key. If you copy an encrypted snapshot across regions, you can't use the same KMS encryption key for the copy as used for the source snapshot, because KMS keys are region specific. Instead, you must specify a KMS key valid in the destination AWS region. So what does that mean? You can copy a snapshot that has been encrypted using a KMS encryption key. So that doesn't really make it clear to me. Instead you must specify a KMS key valid in the destination region, at which point so the thing that I'm trying to figure out here is instead you must specify a KMS key valid in the destination AWS region when you're trying to do what? At which point in the process are you supposed to specify a KMS key valid in the destination AWS region? The RTO of this DR strategy depends on how quickly to restore a DB instance from the copied snapshot. The cost of this DR strategy is mainly the storage cost for the snapshots and data transfer cost to copy these snapshots from your primary region to the DR region. To automate this DR plan, you can use a few AWS tools, such as AWS Lambda and Cloudwatch events. For instance, you can schedule events to trigger Lambda functions to create snapshots of your RDS SQL Server and then copy these to a target DR region. And then here's the next DR strategy, the second one they have in this article, continuous replication. To meet very aggressive RPO and RTO requirements, your DR strategy needs to consider continuous replication capability from your source RDS SQL Server to the target RDS SQL Server in your DR region. Being a managed service, RDS for SQL Server helps automate time-consuming tasks like patches, backups, high availability, and more. However, to ensure availability and durability of the instance, RDS for SQL Server does not allow sysadmin permissions to expose all available engine features. SQL Server MS Replication is one such feature that, as of this writing, isn't yet available in RDS for SQL Server. And I guess that they say the reason that's not available is to ensure availability and durability of the instance. Interesting. However, you can use AWS Database Migration Service, DMS, to do continuous replication. DMS needs MS, CDC, change data capture, to be enabled on the RDS for SQL Server instance. For instructions on enabling this, see Introducing Ongoing Replication from RDS for SQL Server using DMS. The RPO of this DR strategy depends on how quickly the Database Migration Service, DMS, consumes the captured changes that are available from the source RDS for SQL Server instance and applies them to the target. In this DR strategy, the target RDS for SQL Server is active, so that you could have a near zero RTO. However, this active target DB instance incurs additional costs, including the SQL Server license cost. In addition, because the data transfer by DMS in this DR strategy is to a different region, there is a data transfer related cost. For more information, see DMS pricing. So far what I'm hearing is if you want to have an active DR solution for your cross-region needs, then you're going to be paying for the extra instance, for the extra license for that instance, and you're going to be paying for the data transfer cost that is associated with going across regions. Several factors impact the performance of this DR strategy using AWS DMS, such as availability of your primary RDS SQL Server, available network throughput, number of changes that are captured, and the underlying memory, CPU, and I/O on source and target side. The MS CDC feature, which I think means Microsoft Change Data Capture, if we look higher in the article, change data capture. The change data capture feature, MSCDC, that is a requirement for DMS, is supported for both standard and enterprise editions from SQL Server 2016 SP1 and higher. For older versions, only an enterprise edition supports this feature. Testing your cross-region DR strategy. To make sure that your cross-region DR strategy works, you need to test it out regularly. This regular DR testing enables you to identify potential issues or gaps in your DR strategy and take corrective action. After each DR strategy test, you should document the results of your testing and find ways to improve your DR strategy. As your business and application requirements may change over time, you should adapt your DR strategy to meet those changes. Just some general common sense advice here. Regularly testing and continuously improving your DR strategy helps you be prepared and meet your DR objectives if an actual disaster occurs. Conclusion. This post provides two primary approaches to create a cross-region DR strategy of your RDS for SQL Server based upon RPO, RTO, and cost. There will be future enhancements for SQL Server that will make your cross-region DR strategy even more reliable and efficient. And the authors were Changbin Gong, Senior Solutions Architect at AWS, and Rajiv Totatil, a Senior Database Solutions Architect at AWS. And, it said that this is based on RPO, RTO, and cost. It did mention RPO, it did mention cost. I'm curious to see how many times it mentioned RTO. Here it says the RTO of the first strategy, the snapshot and restore strategy, depends on how quickly to restore a DB instance from the copied snapshot. So the RTO of the snapshot and restore DR strategy depend on how quickly to restore a DB instance from the copied snapshot. So that makes sense. So if you want to know how little downtime you can have, meaning like what reasonable RTO is, then you can test how long it takes to restore your database in another region from the snapshot. And then it says in terms of RTO, for the other strategy, the continuous replication strategy, you get a near zero RTO. So that was a useful article. Okay, folks, moving on through this blog post called 10 Study Tips for the AWS Certified Database Specialty Certification by Nigel Harris. And again, I am Yann Stoneman, and I am working on studying for the AWS Database Specialty Certification. And the next resource to consider is using CloudFormation to configure auto-scaling for Amazon DynamoDB. Now I'm going to take a quick look at this because probably I can just look at the code real quick and get an idea for what's involved. So I'm just scrolling through the code here. There's even a button to launch the stack and what it should look like after you've launched it. All right, so the main part of this article is really right here. It says, now comes the auto scaling portion of the template. First, configure the scalable target to set the upper and lower bounds for writes on the user table. So you can call the resource whatever you like. Here it's called user table write capacity scalable target, and the type of this AWS resource, of this AWS CloudFormation resource, is AWS application auto scaling scalable target. Now that's really interesting because usually the type would be like DynamoDB if it's a DynamoDB related resource, but let me look up this resource. So you see you've got different services. It goes by service in CloudFormation: API Gateway v2, App Config, App Flow, App Integrations. And then you've got application auto scaling, and that has two types of resources: the scalable target and the scaling policy. And the scalable target supports a DynamoDB table or an ECS service. And then you've got the scaling policy, and that supports an ECS service, a Spot Fleet, an EMR cluster, an App Stream Fleet, a DynamoDB table, DynamoDB Global Secondary Index, Aurora DB cluster, SageMaker endpoint variant. Custom resources are not supported with a resource type. Amazon Comprehend document classification endpoint. Whoa, and the list goes on. Oh, also Lambda provision concurrency, Amazon key spaces table, and MSK cluster are all supported by the application auto scaling policy resource. And the scalable dimension is just different depending on the service that this is used for. So for DynamoDB table, the scalable dimension is pretty straightforward: read capacity units, write capacity units for the table and for the index. You've got your main table with its read capacity and write capacity units, and you've got your index with its read capacity and write capacity units. So looking at the scalable target, it supports a lot of different resources, but it's different than a EC2 auto scaling group. It's like everything that doesn't neatly fit into the EC2 auto scaling group. So in this example, you've got the AWS application auto scaling scalable target resource with the properties max capacity 100, min capacity 5, resource ID is the table name, the role ARN is the AWS service role for application auto scaling DynamoDB table. The scalable dimension is DynamoDB table write capacity units. The service namespace is DynamoDB, and it depends on table my app user. So you first need to create the DynamoDB table, or CloudFormation first creates the DynamoDB table, and then the application auto scaling scalable target targets that table. And then you've got the other application auto scaling resource called scaling policy, and you give it a name, a type. In this case, it's a target tracking scaling. So I'll read this description of how that policy works. The target value is a percentage that indicates when DynamoDB should scale in or out. This is set to 70, which means 70% of the current provisioned throughput. For example, suppose that the current write capacity unit is 10, and you consume more than 7 capacity units per second for 60 seconds. So you've got the scale in cooldown 60, scale out cooldown 60. A scale out event occurs because the consumption has exceeded 70% of the current setting. The newly provisioned capacity is set to a number that places the current consumption to 70% of the provisioned capacity. If you are now consuming 14 write capacity units, auto-scaling sets the provisioned write capacity to 20 because 14 is 70% of 20. Okay, it's going to change the provisioned capacity so that however you're currently using the database is 70% of the provisioned capacity. It'll be adjusting the provisioned capacity so that you're always using the target value of whatever metric it is. In this case, write capacity units. For optimal scaling, you can tune the scale in cooldown and scale out cooldown values to prevent DynamoDB from being too aggressive about changes that occur over short periods of time. Set the scale out cooldown value as low as possible, but high enough that the scaling metric will have felt the impact of one scale out event before another one begins. Right, so you don't want to have your scale out cooldown value so low that it performs a second scale out event right after the first because the scaling metric hasn't yet caught up. Now you need to create a scalable target and scaling policy for the global secondary index. Right. So just because you create a scalable target and scaling policy for the table doesn't mean that affects the indexes you have on that table. You need to create it for your indexes too. Now I'm curious if that is only for the global secondary indexes, and I believe so because I think only the global secondary indexes get their own provision capacity. So let's look up the word local, and it's not even in there. Global shows up 5 times. Okay, so that's good to know. But I'm also curious to see what Rick Houlihan, I think his name, Nick or Nick Houlihan, DynamoDB, yeah, Rick Houlihan. I'm curious to see what Rick Houlihan at AWS has to say about scalable targets. In the last year, no results. So when was this written? Yeah, the article I'm reading about how to use CloudFormation to configure auto-scaling for DynamoDB tables and indexes was written in early 2018. So at this point, that's over 3 years old. And I feel like at this point, there's a simpler approach, which is just setting it to auto, because I haven't had to deal with that. Okay, this is why I haven't really been dealing with configuring auto scaling for DynamoDB tables and indexes, because a half a year after that article about auto scaling came out, a new feature of DynamoDB was released called On Demand, which lets you do no capacity planning and have pay per request pricing. And that's typically what I use when I use DynamoDB table in real life. I just set it to on demand, and then I don't need to think about 70% and write capacity units. Just set it to on demand. But apparently it might come up in the exam, so now I'm prepared. Alright, so coming back to the 10 study tips, let's see what the next recommended blog post is. Okay, so this is something I might need to know more about. Sharding with RDS. So this article is from the 20th of March 2019, so a little over 2 years old, and it's by Lei Zhang, who is a senior database engineer at AWS. And I feel like sharding is something that happens under the hood in RDS, so I'm curious why I should know anything about it. But let's see. Maybe this is just to prove why RDS works, like if someone's wondering, how are you really able to be so good? Okay, sharding, also known as horizontal partitioning, is a popular scale-out approach for relational databases. Guys, I'm just trying to stay awake while I'm studying, so I'm really going into it now. Amazon Relational Database Service is a managed relational database service that provides great features to make sharding easy to use in the cloud. In this post, I describe how to use RDS to implement a sharded database architecture to achieve high scalability, high availability, and fault tolerance for data storage. I discuss considerations for schema design and monitoring metrics when deploying RDS as a database shard. I also outline the challenges for resharding and highlight the push-button scale-up and scale-out solutions in RDS. The sharded database architecture. Sharding is a technique that splits data into smaller subsets and distributes them across a number of physically separated database servers. Each server is referred to as a database shard. Okay, yeah, why do you need to make up those fancy names like shard? It's just a server. Okay, each server is referred to as a database shard. All database shards usually have the same type of hardware, database engine, and data structure to generate a similar level of performance. However, they have no knowledge of each other, which is the key characteristic that differentiates sharding from other scale-out approaches such as database clustering or replication. Okay, folks, we've got the key difference here. The key difference between database clustering and database sharding is that in sharding, the nodes of the, let's say, cluster don't know about each other, whereas in the clustering technique, they do know about each other. So, moving on. The share nothing model offers the sharded database architecture unique strengths in scalability and fault tolerance. The share nothing model offers the sharded... Oh, okay. So basically, thanks to sharing nothing between each other, you get unique strengths in scalability and fault tolerance, is another way to put that. There is no need to manage communications and contentions among database members. Right. Like if you've got roommates in a college, if they're all living in one room, you might have communication management issues and contentions, but if you've got separate rooms, there's no need to manage that. So the complexities and overhead involved in doing so don't exist. If one database shard has a hardware issue or goes through failover, no other shards are impacted because a single point of failure or slowdown is physically isolated. Sharding has the potential to take advantage of as many database servers as it wants, provided that there's very little latency coming from a piece of data mapping and routing logic residing at the application tier. However, okay, so what's the drawback? The share nothing model also introduces an unavoidable drawback of sharding, and that is the data spreading out on different database shards is separated, right? You don't have all the data in one place. That's the advantage and the drawback. The query to read or join data from multiple database shards must be specially engineered. It typically incurs a higher latency than its peer that runs on only one shard. The inability to offer a consistent global image of all data limits the shard database architecture in playing an active role in the online analytic processing OLAP environment, where data analytic functions are usually performed on the whole dataset. In the online transaction processing OLTP environment, where the high volume of writes or transaction can go beyond the capacity of a single database, the scalability is of concern. Sharding is always worth pursuing. So it sounds like the author here is saying that sharding isn't so great for OLAP because usually everything you're doing is relevant for the whole data set, but sharding is more relevant for OLTP, so not data warehouse, but like just standard relational database, transactional database, because there you need higher scalability and you don't always need to look at the entire database with every transaction. With the advent of RDS, database setup and operations have been automated to a large extent. This makes working with a sharded database architecture a much easier task. RDS offers a set of database engines, including RDS for MySQL, MariaDB, PostgreSQL, Oracle, SQL Server, and Amazon Aurora. You can use any one of these as the building block for a database shard in the sharded database architecture. Let's take a look at an example of a sharded database architecture that's built with RDS. In the context of AWS, its position in the data flow path has several characteristics illustrated in the following diagram. You've got users on the internet on their phones accessing a web application tier in an auto scaling group on EC2, and the application accesses the OLTP tier with Amazon RDS as shard 1, Amazon RDS as shard 2, and the same as many as you want. And each of those RDS shards has a database instance and a database instance standby. And then that can also replicate to an OLAP tier analytics that can be on Redshift and S3. So to go into more detail on this diagram, data is entered into the system through web applications that are hosted on a group of EC2 instances with the auto scaling feature. Data storage is layered, where the OLTP environment is separated from the OLAP environment to meet different business and ownership requirements. Yeah, you use the right infrastructure, separate your OLTP from your OLAP infrastructure. The OLTP environment uses database sharding. It consists of a group of databases built with RDS for high scalability to meet the growing demand for write throughput. Each database shard is built for high availability using a standalone database deployed with the multi-AZ feature. Note, if you choose an Aurora DB cluster to build a database shard, you can also achieve high availability by configuring a read replica with the primary instance. Data is pulled from the OLTP environment into the OLAP environment based on a schedule. Yeah, because you don't need to pull reports from your OLAP environment all the time. You can do it based on what's relevant for your analytics needs. You can use Amazon Redshift to accommodate data from all database shards and construct a time-consistent global data set for data analytics functions. Aggregated data result sets are pushed to S3 for data sharing, other analytics services, and long-term storage. Data partitioning and schema design. The prerequisite to implementing a sharded database architecture is to partition data horizontally and distribute data partitions across database shards. You can use various strategies to partition a table, such as list partitioning, range partitioning, or hash partitioning. You can allow each database shard to accommodate one or more table partitions in the format of separate tables. The following diagram is an example of horizontal partitioning in the invoice table with customer ID as the partition key. So here you've got a diagram with horizontal partitions where the customer ID is the partition key, and sharding happens based on the partition key. So 1, 2, and 2 for customer ID 1 and 2. You've got database shard 1. For customer ID is 3 and 4, you've got database shard 2. So this is an example of horizontal partitioning. When multiple tables are involved and bound by foreign key relationship, you can achieve horizontal partitioning by using the same partition key on all the tables involved. The data that spans across tables but belongs to one partition key is distributed to one database shard. The following diagram shows an example of horizontal partitioning in a set of tables. Okay, let's take a look. This might help it make more sense. So you've got a partition key. Okay, yeah, so customer ID 1 and 2 goes on shard 1. And customer ID 3 and 4 goes on shard 2. That is the mapping and routing logic at the application tier. Okay, gotcha. So the application is aware of this sharding logic, and if it has a customer of ID 1, it knows to write it to the database shard 1, and if it's trying to read or write data related to customer 4, the customer with ID 4, it knows, okay, I've got to access the database shard 2. With a structure like that, you want to use that partition key basically for all of your tables. Even though in your invoice table you have an invoice ID, it's the customer ID that determines which shard that invoice entry is written or read to or from. So here are a few bullets about that diagram. The basic design techniques used are as follows. Each database shard contains a partition key mapping table, customer, to store partition keys that reside on that shard. Oh, okay, so that means that on a database shard, it'll say, I've got customer 1 and 2, that's me. And then on another shard, it'll say, over here, I've got customer ID 3 and 4, that's me. So that's what the partition key mapping tables do on each database shard. Applications read this table from all shards to construct the data mapping logic that maps a partition key to a database shard. Oh, okay. So this mapping and routing logic table on the left here is created from that partition key mapping table, which I don't think is included here. I guess basically this top half of this diagram would live on the database shard 1, and this bottom half of this mapping table would live on database shard 2, and then the application grabs that partition key mapping table from each shard to construct the complete table so that it knows which shard to go to for which partition key value. Sometimes applications can use a predefined algorithm to determine which database shard a partition key is located in, and so this table could be omitted. Oh, okay, so I guess there are some predefined algorithms that use a certain logic to determine which database shard has what, and then you can just use that algorithm instead of referencing a table in the application. The partition key, customer ID, is added to all other tables as a data isolation point. Right, that's what we saw here. So even in other entity mapping diagrams, EMRs, you might not have one key used in, or one ID used in every table. Like here, you've got the deliver ID, several of them, but not on each of them. And there's no ID that shows up on each single table. But with this horizontal sharding approach, you've got one ID that's on all of the tables. In this case, customer ID. The partition key customer ID is added to all other tables as a data isolation point. It has direct influence on data and workload distribution to different database shards. Queries intended for a single partition include the partition key so that the data routing logic at the application tier can use it to map to a database shard and route the queries accordingly. Right. If the application is intending to only query from one database shard, then it will include the partition key, in this case customer ID, to route the query to that database shard. Primary keys have unique key values across all database shards to avoid key collision when the data is migrated from one shard to another, or when data is merged in the OLAP environment. For example, the primary key of the invoice table, invoice ID, uses interleaved numbers and has the last 2 digits reserved for the shard ID. Another common practice is to use GUID or UID as primary key. Okay. So here with the invoice tables, you might have an invoice 51 on the invoice table of both shards, but then you add the primary key at the end, 01 and 02, so that if you combine both shards in an analytical environment, that you don't get key collisions. The column with the timestamp data type, okay, let's look at that one. Okay, so like creation date, that has a timestamp data type, can be defined in tables as the data consistency point. Okay, so we've got the data isolation point, which in this case is the customer ID, and the data acts as the partition key. And then we've got the data consistency point, which could be the timestamp. It acts as the criteria to merge data from all database shards into the global view when necessary. Right, okay. So when you want to create a unified view of all of this, you can put them into one huge database, like a data warehouse like on Redshift using the creation date in this to order it, and that's why it's called the data consistency point. For example, when data is pulled into the OLAP environment, the creation date of the invoice table is used as a filter in the pulling query to specify a consistent time range for all shards. Right, because then the Redshift query can be like, give me all the data between January and March of last year. A well-designed shard database architecture allows the data and the workload to be evenly distributed across all database shards. Queries that land on different shards are able to reach an expected level of performance consistently. The increasing number of data partitions on a shard would raise a database engine's resource consumption, building up contention spots and bottlenecks even on large-scale hardware. To decide how many data partitions per shard to use, you can usually strike a balance between the commitment to optimize query performance and the goal to consolidate to get better resource use for cost cutting. Right, if you have unlimited amount of money, you could just have a ton of shards. When deploying RDS as a database shard, you must also consider the type of database engine, DB instance class, and RDS storage. To help you easily manage database configurations, RDS provides a DB parameter group. It contains the desired set of configuration values that can be applied to all database shards consistently. I want to get a quick review of what some of the options for the DB parameter group are. I know how in another article in preparing for the database specialty exam, it mentioned the RPO RDS database parameter for the Aurora global databases. So here's some examples of parameters for MySQL in RDS. You can have auto commit true or false, automatic SP privileges true or false, auto increment offset, which is integer values. So it just depends on which database engine you're using, and you want to make sure if you're sharding, you know that all of your shards have consistent values, and that's why RDS provides the DB parameter group, so you can apply the same parameter group across all the databases that meet the same configuration. Monitoring for scalability. Monitoring metrics from one shard, such as system resource usage or database throughput, are considered more meaningful in the context of a global picture where you can compare one shard with others to verify whether there is a hotspot in the system. It is also beneficial to set up an appropriate retention period for monitoring data. You can then use historical information to analyze trends and plan capacity to help the system adapt to changes. Right, because you might see like every Friday when people are doing more shopping or whatever on your website, the database gets more load, and then you can plan your capacity accordingly. As a managed service, RDS automatically collects monitoring data and publishes it to Cloudwatch. Cloudwatch provides a unified view of metrics at the database and system level. Some metrics are generic to all databases, whereas others are specific to certain database engine. For a complete list of metrics, see the docs. I always recommend metrics that monitor overall system resource usage, such as CPU utilization, freeable memory, read IOPS, write IOPS, and free storage space. These metrics are indicators of whether the resource usage on a database shard is within capacity and how much room remains for growth. System resource consumption is an important factor to justify that a sharded database architecture either needs to be further scaled or consolidated otherwise. The following example is an example Cloudwatch dashboard that offers great visibility into the sharded database architecture. It brings real-time and historical metrics data from all database shards together into one graph. Yeah, I think that's helpful when you create a dashboard to group related resources together on a single metric like CPU utilization, so you can see shard 4 has more CPU utilization spikes than the other shards, whereas shards 2 and 3 have higher freeable memory. When a database shard has high system resource usage and requires more horsepower, it can be either scale up or scale out. Yeah, okay. So basically that means if you need more power, you either scale up or out. RDS provides a push button scale up option, meaning you can just, make it go from an R5 extra large to R5 2x large. You can use it to modify a DB instance class to larger hardware with more CPU and RAM, or modify DB instance storage for more storage space and increased IOPS capacity. The choices of available instance classes might vary for different database engines or specific database versions. The AWS Management Console is a good place to check that. Yeah. If you choose RDS for MySQL or PostgreSQL to build a database shard, there is another scale-up option. Migrate to Aurora. An Aurora DB cluster can consist of more than one database instance on top of clustered storage volumes to deliver higher performance and IOPS capacity than an RDS DB instance. RDS provides a push button option to create an Aurora read replica. This option sets up the replication process to migrate data from RDS DB instance for MySQL or PostgreSQL to an Aurora read replica. In other words, they make it as easy as possible to move over to Aurora, which has higher performance. When the database migration is complete, the Aurora read replica can be promoted to be a standalone Aurora DB cluster. Resharding. So I guess this is about oops, I didn't do it right in the first time, or my needs have changed. How do I change my sharding strategy? So let's read this section. The scale out option for a database shard is known as resharding, meaning sharding again. Yeah. In a broad sense, resharding can also refer to all the procedures that intend to adjust the number of shards in a sharded database architecture. Okay, yeah, basically resharding can mean anything that has to do with tweaking the number of shards. These procedures, including adding a new shard, splitting one shard into multiple shards, or merging multiple shards into one. Despite their different format, those procedures essentially need to perform the same type of operation to migrate existing data from one shard to another shard. Okay, so resharding is basically a very specific type of migration. In a live production database where data is constantly being accessed and changed, data migration with minimum downtime is always a challenge for resharding. RDS has made a great effort to make resharding easier. In RDS for MySQL, MariaDB, or PostgreSQL, RDS provides a push-button scale-out option, read replicas, to split one standalone database into multiple new ones. The following diagram shows an example workflow of resharding that uses a read replica as a data replication technique to migrate data between databases. Okay, so basically, when you're doing resharding with RDS read replicas make it easier. Step 1. Create read replica. Step 2. Promote read replica to be a new shard. Step 3. Route connections to new shard. Right, and the nice thing with read replicas is that it'll constantly be updating from the old one. So here in the diagram of that, we've got Amazon RDS as shard 1 with its DB instance and DB instance standby pointing at DB instance read replica, and you've got mapping and routing logic at the application tier. And then once step 3 happens, it means that at the application level, if you used to point customer IDs 1 and 2 at shard 1, now you point customer ID 1 at shard 1 and customer ID 2 at shard 2, for example. So to describe this diagram, the author here wrote 1. The read replica is created to replicate data from the master database continuously. And then 2, the master database holds off writing activities so that the read replica can sync up and be promoted to be a new standalone database. During this time, the mapping and routing logic at the application tier updates the status of multiple data partitions on the master database to be read-only. Okay, to me that sounds like a little bit of downtime, and during that downtime you don't have any write activities. You promote the read replica to be a standalone database, and you update the mapping and routing logic of the application so that when things come back online, now customer ID 2 points at shard 2. If you choose an Aurora DB cluster to build a database shard, its read replicas share the storage volumes with the primary instance. Therefore, they cannot be used to replicate data between Aurora clusters. Instead, RDS provides the clone database feature to create a new Aurora DB cluster with the same data as the source database. From an Aurora MySQL database cluster, there is also an option to set up MySQL replication to replicate its data to another new Aurora MySQL database cluster. I just want to take a quick look at this MySQL replication. Right, and this is like a MySQL native kind of thing. In addition to using existing database technologies to replicate data, Resharding can also take advantage of other tools to migrate data between database shards, including DMS, or user-defined data extract processes. The following diagram is an example of a tool-based resharding workflow that migrates one data partition at a time. Okay, so that last paragraph sounds to me like, don't worry, there's help out there. We've got tools. There are third-party tools or custom tools, bespoke tools you can make, or our very own database migration service can help with this. Because again, resharding is pretty much a data migration. So here we have another diagram, and in the step 1 it says the data migration tool is set up to replicate a data partition from one database shard to another. The mapping and routing logic at the application tier updates the status of the data partition to be read-only. The data migration tool can then sync up the data between the two database shards. After the data is in sync, this is step 2 now, the data mapping and routing logic at the application tier updates the mapping and status of the data partition so that it goes live on the new database shard. Folks, just use DynamoDB and spare yourself all this headache. Okay, I'm trying to understand why this is only a 2-step process and the other one was a 1-step process. To me, it seems like it's still a 3-step process. They just kind of merged the setting up a replication shard. Yeah, this looks like 2 steps here in step 1. So it's just that you've got kind of more assistance with the replicating data part of it by using a tool. The tool-based resharding method has flexibility because each data partition can be migrated individually. While one data partition is being migrated, it is brought into read-only mode and applications can still read its data. Other data applications remain accessible for both read and write, and the availability of the overall sharded database architecture can be guaranteed. So I don't really understand why with the first method, each data partition cannot be migrated individually, and with the tool-based resharding method, it can. I'm trying to understand that. So that's kind of an open question for me. The database-based resharding method places the downtime of write activities on multiple data partitions on a database shard when it comes to spin off a new database. After the new database is live, it contains all the data partitions replicated from the original database, even though only some of them will be used on it. Therefore, you will need to clean up the duplicated data. It seems like that's a very heavy-duty summary of a lot of hard work, so I'm just gonna leave it at that. But it seems like there's a lot packed into that last paragraph, so I'll just read it one more time to really get it a little better. The database-based resharding method, as opposed to the tool-based resharding method, places the downtime of write activities on multiple data partitions on a database shard when it comes to spin off a new database. After the new database is live, it contains all the data partitions replicated from the original database, even though only some of them will be used on it. Therefore, you will need to clean up the duplicated data. Okay. So I guess the migration tool can kind of be aware of some of the partitioning logic, and therefore you don't need to take care of that deduplication yourself. So in summary, in this post, you read about sharding as an approach for relational databases to achieve high scalability. You learned about an example use case that uses RDS to implement a sharded database architecture in the cloud and how it fits into the data storage and analytics workflow. You also learned about various features that RDS provides to manage, monitor, scale up, and scale out database shards in a highly automated manner. So, when I read all this, I'm like, please use DynamoDB, folks. Like, read Rick Houlihan's posts. Like, there's a lot of stuff you can do in DynamoDB that, people thought is something you have to do in a relational database. Well, the fact is, you can use DynamoDB in a relational way, even with a single database design. Look up single database design, so you don't have to have this headache of sharding. But I was curious, like, what's the latest on sharding, and found this article here. RDS now supports, in February 12th, 2021, replication filters for MySQL and MariaDB instances. Replication filters specify which databases and tables are replicated in a read replica. Customers create lists of databases and tables to include or exclude for each replica. Replication filtering can reduce the size of read replicas by excluding unnecessary databases or tables, or can benefit security and compliance by excluding databases or tables from a replica. Customers can also use replication filtering to create replicas tailored to specific use cases like analytics or sharding, or to create replicas with different tables or databases in different AWS regions. Sounds interesting, because if you've got replication filters and you're trying to do sharding, you can just do replication to the new database shard of exactly what you want that shard to then be used for. So that sounds useful. But in general, there are not a lot of results about when I type in sharding and RDS on Amazon.com. If you have to use RDS, use Aurora. Like, look, the Pokemon company here, by switching to Aurora, they went from 300 nodes to 30 and got to stop paying for database licenses, and they migrated database shards to Aurora. Database shards contain the master database of Pokemon creatures, trading card game, online user data, and data from in-person organized play groups. Anyways, use DynamoDB, use Amazon Aurora, use the latest and greatest from the cloud. In many cases, that'll spare you the pain of doing all this manual work with sharding to get higher performance. You can just get higher performance by moving to Aurora or DynamoDB. And obviously it's not like either or with Aurora, but if you move to Aurora with its higher performance, you just might not need the sharding, even though you could still do it with Aurora. So obviously there's a ton more to cover for the AWS database certification. This was not meant to be an all-inclusive video, but just kind of a study with me video. And if you like this video, please give it a like and subscribe, and leave a comment for what kind of videos you want to see in the future. Wish me luck on my database certification exam tomorrow morning at 6:45 a.m. I wanted to do it before too much starts happening in the house with the other folks. So leave a comment below and let me know what your preparation for the database specialty certification was like.